G'day. This presentation summarizes my assessment of a 50-year-old reinforced concrete bridge near chemical factories. The inspection photograph shows rust staining, leakage path, spalling, lamination, cracking, and exposed reinforcement at deck edge, beam end, headstocks, and piers. The key deterioration mechanism is moisture and industrial pollutant ingress. Chlorides and sulfates combined with poor drainage and repeated wet dry cycling and depassivate the reinforcement. Corrosion products then expand, causing cracking, lamination, and loss of concrete cover. My assessment sequence was to inspect and map the defects, recommend testing, repair the deteriorating source, compare strengthening options, and use preliminary space gas model to check global behavior. The main message is that strengthening should not be the first action. The defect cause must be controlled before CFRP steel plate strengthening can be durable and reliable. The report treats the bridge as 5 representative deterioration zones: deck edge and beam end deterioration, pier spalling with vertical cracking, headstock delamination unit supports, rust staining and leakage path, and soffit deterioration with possible concealed delamination. The recommended testing is targeted rather than excessive. Half cell potential and resistivity testing are used to map active corrosion risk. UPV, impact echo, or hammer sounding are used to identify hidden delamination. Cover meter scanning is required before drilling or anchoring, and limit chloride and carbonation samples confirm chemical deterioration mechanism and repair depth. The refurbishment strategy follows the repair before strengthening sequence. Drainage and waterproofing are corrected first. Unsound concrete is then removed. Corroded reinforcement is cleaned or supplemented, and the member is reinstated with compatible Class R4 repair mortar before curing and protective coating. CFRP is preferred for soffit and deck edge because it is light and corrosion resistant. Steel plate or jacket remains useful at headstock, bearing, and local support zone, where robust mechanical restraint is required. For modeling component, I used a simplified 20-meter simply supported 2D space gas model. The deteriorated bridge was represented using C20, C25 concrete and corroded reinforcement, with 20mm bars reduced to an effective 18mm diameter in a critical zone. The applied action include concrete dead load, asphalt overlay, pedestrian load, and the SM1600 moving load envelope. The deteriorated model produced a maximum combined surface deflection of 14.9mm below span over 500 limit of 40mm. However, the bridge is not acceptable on deflection alone because corrosion, delamination, and spalling remains active. Durability and safety risk. CFRP strengthening reduced deflection to 12.7mm, a 14.7% improvement. Steel plate reinforcing reduced it to 11.7mm, a 21% improvement. Although steel gives the highest stiffness increase, I recommend CFRP for soffit and deck edge flexural strengthening because it adds little dead load and is not vulnerable to corrosion. Steel strengthening should be used selectively at headstock, bearing, and support zone. Final design must still check crack width, flexural, and shear capacity. CFRP, debonding and anchorage, and construction staging. Thank you.